Okay. So for the power of a power property, we said that all we really are doing here is multiplying the two exponents together. When you're raising a power to a power, and you can see exactly why you would do that, because x squared to the fourth is x squared times x squared times x squared times x squared, which is x to the eighth. You can get there by just doing 2 times 4. So without having to write all of it out, what would 5 to the first to the third power be? Sky? That's right, 5 to the third. Of course, 5 to the first is just 1. Oh, no, sorry. 5 to the first is just 5. So that would just be 5 to the third. What about 6 to the third squared? 6 cubed squared. What would that be, Jimmy? That's right. And b to the fifth cubed. Dawson? B to the 15th. That's right. Okay. So when raising a power to a power, multiply the exponents together. And then finally, we have the power of a product property. And this is the one we were kind of just looking at with that pyramid, where it was 3 halves b, and we were squaring that entire quantity. If you have a factor of 2 things in parentheses and you're raising that to a power, let's see what happens. This one here, first of all, what is 2 times 3? 6. Okay, so we could say this is 6 to the third power. Obviously, that'd be pretty simple. But there's another way of thinking about it. You could actually distribute the exponent to both of the factors in the parentheses, and you could think of it as 2 to the third power times 3 to the third power by distributing that exponent. 2 to the third power, just so you know, is 2 times 2 times 2, which is 8. And 3 to the third power is 3 times 3 times 3, which is 27. And 8 times 27 is 216. Guess what 6 to the third is? 216. So as how you would write this as a power, I'm guessing they're probably going to want you to write it like this, just because that's what the property entails. But that's proof that you actually get the same thing. 6 to the third would give you the same answer as 2 to the third times 3 to the third. 2 to the second times 5 to the second, which is what they want you to write here, is 4 times 25. What's 4 times 25? 100. What will you get if you do 2 times 5 and then square that? 100. 10 squared is 100. So you get the same answer. So let's actually use that with some variables. So this makes a little bit more sense. If I have 6a and that is all being raised to the 4th power, I'm going to distribute the 4 to the 6 and distribute the 4 to the a. So that would be 6 to the 4th, a to the 4th. Now they're probably going to want you to simplify 6 to the 4th. What is 6 to the 4th? You'll need your calculator for this, unless you know 36 times 36. I mean, you could think of it as 6 squared times 6 squared. That's 6 to the 4th, but that doesn't really help me because I don't know my 36 is that high. What do you get, Dawson? 1,246? 1,296? Okay, so they're going to want you to write this as 1,296, simplify the 6 to the 4th part, and then a to the 4th still being multiplied. Just like in our problem we looked at with the pyramid, 3 halves b all being squared, we wanted to write that as 9/4 b squared. What about this one? If I have 3x squared and I distribute that, what's 3 squared? 9. And then of course, x squared just be written right off to the side there. Or you could think of it as 3 times x times 3 times x, if you wanted to think of what it actually means to square it. And then you just rearrange that, and that's going to give you 9x squared. Okay. So essentially, what we're saying is when you're raising a product to a power, so it's called the power of a product property. That's a lot of p's. You're distributing the 5 to the 3 to get 3 to the 5th, and you're distributing the 5, the exponent, to the 2 to get 2 to the 5th. Okay, or using letters, you can see distributing the m here and distributing the m there. So those are the 4 properties we're going to talk about in sections 10.2 and 10.3. So what we're going to do now is we're going to review all 4 of these properties that I've got color coded in red, blue, green, and purple. We're going to review all the properties, and then we might get to today. We'll see if we have time. Maybe not, maybe for tomorrow. What happens when we have negative and 0 exponents? If you've gotten past 10.2, 10.3, and you've dipped into the 10.4 homework, you've seen 0 and negative exponents. We may not get there today. That's okay. We got time tomorrow to get there. All right. So 2 to the 4th times 2 to the 5th. The instructions say simplify each expression and write our answer as a power. So they don't want us to actually evaluate this. I'm not going to get an answer like 12,237. I'm going to actually write it as a power. So what do I do when I'm multiplying 2 powers that have the same base together? What do I do here, Owen? Add the 2. This whole thing's called a power. Exponents, that's right. And what would that give us as our final answer then? 2 to the 9th. Nice job. How about this next one? Negative 1/2 to the 3rd times negative 1/2 to the 6th. Chloe, what is that going to give us as a power? That's right. Negative 1/2 to the 9th. Is it important that I write the negative 1/2 in parentheses? Yes, it is. Yep. Not only because it's a fraction, and because it's negative. Yeah, so actually 2 reasons you're going to want to write this in parentheses. We have to write fractions and negative bases in parentheses. The next one, Lucy, how about z times z to the 12th? That's exactly right. Z to the 13th. Remember, z to the nothing is just z to the 1st. Okay, if there's no exponent there, you can assume there's a 1, and you're just going to combine that z with the 12 other ones you already have. Yeah, so that's what that study tip there says. 9 to the 7th divided by 9 to the 4th. Garrett, 9 to the 7th divided by 9 to the 4th. 9 to the 3rd. That's right. How did you know it's going to be 9 to the 3rd? That's right. When you're dividing powers with the same base, you subtract the exponents. That's exactly right. One common mistake, this one's trying to keep you from doing, is when you do this, remember you're not dividing the 9s. You're just subtracting the exponents. It's still going to be a power of 9 to the 3rd power. Example E, h to the 7th divided by h to the 6th. What do you think, Carter?
It's going to be
You're not going to divide the exponents. Not going to multiply them. Garrett, what do you do with the exponents again? You just said it. You subtract them.
oh, so h to the 1st power.
That's right. H to the 1st power, which is actually, you could also just say h. Hello? No, I didn't. All right, yeah, so when you're dividing the powers, it's just subtract the exponents. What about example F? Negative 7 to the 9th divided by negative 7 to the 3rd. Maddox, what would you get for that? That's right, negative 7 in parentheses there to the 6th. Good. Now we're going to raise a power to a power. Jace, y squared to the 4th. What do I do with the exponents now?
You multiply them together.
That's right. When you're raising a power to a power, you don't add them, you don't subtract them, you multiply them now. So what are you going to get for this one, Jace?
Y.
That's right. You can see why I wanted to. I mean, once you get going, you can see that the rules are pretty simple. And that's why I thought this would just be like one combined lesson. W to the 4th to the 5th, Oliver, what would that be? That's right. W to the 20th, 4 times 5. Good job. Now we have a product that's being raised to a power. A product that's being raised to a power. Lizzie, what do you do with the exponent 4 here? That's right. Yeah, it's think like you're distributing it, right? So it becomes 5 to the 4th, y to the 4th. And then Lizzie, I want you to tell me, since we're just going to simplify this, what is y to the 4th? I'm sorry, what is 5 to the 4th? That's right, 625. Y to the 4th, I would simplify my answer all the way down to that. Of course, 5 to the 4th is 5 squared times 5 squared. And you know from doing your perfect squares that 25 times 25 is 625. All right, next one. A squared B, all raised to the 3rd power. Who wants to try this one? Christian? That's right. Nice job. Yeah, so we're distributing the 3. And so what we're doing in our brain, we're imagining that we're doing a squared and raising that to the 3rd power. And then we're doing b and raising that to the 3rd power. And so a squared to the 3rd power does become a to the 6th. That's right. So when you distribute that exponent, if there's already an exponent there, you're going to multiply it to it, just like you did when you raise a power to a power. Example K, negative 1/3 mn, all squared. Brady, walk me through this one. I agree with the 1/9, but what's a negative times a negative? It's going to go positive this time, isn't it? Remember we talked yesterday about even exponents. If you have a negative base raised to an even power, it's going to make it positive now. Keep going. That's right. 1/9 m squared n squared. Good job. Now we're going to combine a couple of these properties together. Xander, you want to give this one a shot? Walk us through. There's actually a couple different ways you could do it. Walk us through how you're thinking.
Well, I would do the top part of the equation.
Okay.
Add those together, getting 3 to the 6th power. Then subtract the 3rd power. Get 3 to the 3rd power.
That's right. Nice job. So you can do the entire top part of the fraction first and simplify the numerator to get 3 to the 6th. Then you can subtract the exponents because you're now dividing. That's what a fraction is a miniature division problem, and get 3 to the 3rd. Was anyone thinking of a different way to do this one? Or can you think of a different way to do this one? Really, you're all that closed-minded. What if you did this part first? 3 to the 4th divided by 3 to the 3rd. That'd just be 3 to the 1st power, right? That just give you one of those 3's left. And then that 3 to the 1st power gets combined with 3 to the 2nd power to make 3 to the 3rd. So you've got a variety of different options of doing this. It doesn't have to be done all the same way each time. Okay, example M. 2 to the 15th divided by 2 cubed times 2 to the 5th. Connor, walk me through this one.
Multiply the 2/3.
Okay, what's that going to give you as the denominator? Not 15. When you're multiplying the powers, you don't multiply the exponents. You would do that if you were raising a power to a power. Who can help Connor out? What do you do with the exponents, Owen, when you're multiplying powers? Add them. So what's that going to be on bottom then, Connor? 2 to the 8th power. Good job. Now finish it from there. What do you do when you're dividing? That's which is 2 to the, got it. Yep. So 2 to the 3rd times 2 to the 5th. Think of it as 2, 2, 2, and then 2, 2, 2, 2, 2. 2 to the 8th on bottom. And those 8 are going to cancel out with the 15 up above, leaving you just 7 2's. 2 to the 7th power. I mean, you literally could write it out. That's just a lot of 2's to write out. Okay. This one, there's, again, a couple different ways you could go about this one. I'm going to let Martin walk me through how he might solve this one. Gotcha. So you're saying, let's simplify the first fraction to 5 to the 5th. Gotcha. Okay. Sounds good to me. Nice job. Yep. So Martin's route was go ahead and simplify each fraction, then multiply them together. But when you multiply fractions, you can actually multiply across top and bottom. So there's another way you could do it too. You could try to multiply across top, bottom, and then save the dividing part, which is subtracting the exponents for the end. That would work too. In fact, if you did that, you'd get 5 to the 14th over 5 to the 6th. And if you subtract 14 and 6, you'll get 8. Okay. So more than one way to do that one. Alex back there. I haven't heard from you yet today. Go ahead and walk us through how you do this one.
So you put that, fractions and then subtract them to get a more rows. And then do the same thing on the other one.
Perfect. Nice job. Seems like that's the way a couple of you guys prefer, is to simplify each of those fractions and then multiply. I guess we are going to get them. We got out of here today. 55. We got 5 minutes. How much of our notes do I have left? A decent sized chunk. It might be good to go ahead and get through this in 5 minutes. Well, at least what we can. All right. So negative and zero exponents. First of all, they exist. You may not have seen them before, but they exist. So far, the problems we've had have all had positive exponents. It is possible to have not positive exponents. For example, you're familiar with the place value chart. You've got the thousands column, the hundreds column, the tens column, the ones column, and you know the other ones on the other side of the decimal to be the tenths, hundredths, thousandths, 10,000ths, all ending in a th. Well, according to this chart, what do you think the ones column would be if you wrote it as a power of 10? Follow that pattern there, Maddox. 0. Yeah. And that shows you, if you know 10 to the first is 10, 10 to the 0 power is actually 1. 10 to the third power is 1,000, 10 to the second power is 100, 10 to the first power is 10, and 10 to the 0 power is 1. Again, following this pattern, what do you think the next one would be? 1/10. How would I write that as a power, Julia? Yeah, 10 to the negative first. 1/100th. 10 to the negative second. 1,000th. 10 to the negative third. So negative exponents are going to be talking about, we're going to be talking about smaller numbers. If you have a power raised to a negative exponent, we'll be talking about smaller numbers, ones that occur on the other side of the decimal point. So these will all be small decimal, or you could write it as a fraction. I mean, I can write 100th as 1 over 100, or you could write it as 0.01. Okay. Now, these negative exponents exist other than just being powers of 10, because we work in a base 10 system. Every time you slide the decimal point over, it increases by a power of 10 or decreases by a power of 10. And what that's doing is it's increasing or decreasing the exponent there. What I'm going to try to show you today, in my short amount of time left, is that when you have a number raised to a negative power, essentially all you're doing is reciprocating it. Do you know what the reciprocal of a fraction is, Owen? So if this is 10 to the third, what's the reciprocal of 10 to the third? What's the reciprocal of 10 to the third? Shane? Say it again. Okay, yeah, sure. You mean like 1 with a 3 being on bottom now? Yes. That's essentially what a negative exponent does. It's going to reciprocate it. So 10 to the negative third is 1 over 10 to the positive third, which is 1, in this case, 1/1000th. Okay. Now, before we get there, let's talk about zero exponents. 5 times 5 times 5 over 5 times 5 times 5. They all cancel out. What happens when everything cancels out? What do you write as your answer? Xander? 1. 6 times 6 over 6 times 6. What's 36 divided by 36? 1. Anything raised to the 0 power other than 0 itself, which we already talked about is 0. Anything, any other number raised to the 0 power is always going to be 1. And if you're like, how is that possible? Right, there's the proof. Everything cancels out, you're left with the number 1. Got to be something left behind. Okay. Well, because the bell's getting ready to ring, let me just go ahead and skip to that negative part. I saw some funny faces, like, what do you mean reciprocate? 4 to the negative second is the same as 1 over 4 to the positive second. What's 4 to the second? 16. So 4 to the negative second is 1/16. You see how that works? Okay, that's going to get you started for those of you wanting to start 10-4. Okay. All right, we'll talk more about this tomorrow. I'll see you guys later.